study of magnetic thin film phenomena. I am Samantha Campos.
I'm Abdul Giabala. I'm Byron Munoz.
I'm Andrew Allen.
I'm Salvador Perez.
And we are Team Carman.
So for the past couple of weeks, we have been working in the active materials lab under the supervision of our advisor, Wei Sun, and Professor Carman. So today we're going to talk a little bit about the goal of our project, as well as give you guys some background information so you can understand it a little bit better. We are also going to describe the tests and procedures we did, and then we are going to explain the results and exactly what they mean. So to begin with, what we did was we made thin film samples, and we also saw how the magnetic interaction between these layers can help advance technology and go from very large, huge, space-consuming and energy-consuming memory storage devices to very small, very energy-efficient memory storage devices. Abdul is going to give you guys a little bit more background information so you can understand a little better.
Thank you, Samantha. My job today is to describe and to explain to you the scientific concepts behind the development of these nano-sized magnetic memory storage devices. Back in 1956, two scientists by the name of Meiklejohn and Bean made a groundbreaking, revolutionary discovery in the world of magnetics and how thin layer magnets interact with one another within this paper. They pioneered and they realized that between two magnetic thin layers, that at the point of their interfaces, the magnetic moments align and lock into place. And this magnetization has now been widely accepted and known and has been studied as the concept of exchange bias. It is the interaction between two magnetic layers and allows for the exchange coupling between them. In order to achieve this exchange bias, these samples have to be prepared and prepared at specific temperatures, which we'll get at a later time. Now, the magnetic moments that are locked in place and in a specific direction give a shift in the hysteresis loop of this magnetization. Now you're probably wondering, what does this idea of exchange bias and these ideas of magnetic moments that are locked in a specific direction have to do anything with memory storage? Well, if you think about what memory storage is, there are an array of switches. Switches that move from one position to another and store or not store memory when a current that has information passes through it. Back to the idea of exchange bias. We saw how the magnetic moments of the magnetic thin layers were aligned and locked in one position. What if we move those positions? What if we're able to create a magnetic switch now between and using the magnetic moments of these thin layers? Originally, the magnetic moments of these particles want to align on the long axis of the thin layer films. Now, once a current that has the information travels through these films, that magnetization switches from one state to another. And that gives us the two switching, that gives us the ability to store or not to store information as it passes through. And this is all said as a concept. Now let's see how we will go about actually creating this. And with more information on that, I'd like to give it up to Byron Munoz.
Thank you, Abdul. Now, the following is an image of the material we worked with in our research project. It was composed of a first layer titanium cap, a second antiferromagnetic nickel oxide layer, a third ferromagnetic nickel layer, another titanium cap, and finally the substrate layer, which was composed of silicon. The following is a procedural description that depicts the day-to-day work that was performed by our team at the Active Materials Laboratory for our research project. First and foremost, before beginning any part of our procedure, we made sure to put on the proper lab attire. Afterwards, the first step was to cut a sample from our material. Using a diamond tip pen, we made a small edge perpendicular to the edge of the material. Due to the composition of our material, we were then able to place that over an Allen key, making sure to align the initial edge with the edge of the Allen key. Once again, due to the composition, all we had to do was gently hold down one end of the material and push the other end down, and the sample would break along the edge of the Allen key. The piece that was to be used as that was to be magnetized was marked to indicate the direction in which the magnetic field would be applied. Afterwards, we placed this sample on an induction heater and placed that induction heater between the magnetic plates of an electromagnet. We made sure to adjust the yolks of the magnetic plates to account for the variable air gap. Then we turn on voltage to heat our sample and consistently measure the temperature of the sample using a thermocouple sensor. Once the temperature of the sample reached the desired amount, which were 210, 220, 230, 240, and 250 degrees Celsius respectively for all our trials, we proceeded to turn off the voltage. We turned on the chiller and set the electromagnet to 60 Oersted, which was the unit of magnetization for the, and afterwards, we let the sample cool to about 50 degrees Celsius, and once it reached this point, we turned off the chiller and the electromagnet and placed our sample on a cooling block. Afterwards, we took the sample once it had cooled, cut a piece approximately 5 millimeters by 5 millimeters using the same techniques as mentioned before, and we placed that small piece in a container that would later be transferred into the superconducting quantum interference device. We have some samples here with us, and Abdul will pass those around. Now for the squid procedure, once we arrived at the superconducting quantum interference device, which will hereby be referred to as the squid due to its lengthy name, we first purged the sample space to allow ourselves to place our own sample in the squid. Then we centered the sample within the squid. We took the time to set the magnetic field to approximately 100 Oersteds, and we set the code for the length of the sequence. We allowed this sequence to run, and it collected the data of exchange bias of our samples. And here to follow up and elaborate on the interpretation of this data is Andrew.
Thank you, Byron. All right, so appearing up on the screen, there we go. We should have the results of the samples that we tested for exchange bias. So just to briefly describe to you what these graphs are showing, what each axis means, we're essentially plotting the average magnetic moment, which is a fancy way of saying the magnetization of our sample, against the applied magnetic field on the horizontal axis. And you can see that we did this for samples that were heated up to various temperatures, from 200 degrees Celsius up to 250 degrees Celsius. Now, a couple of things that we can deduce from these graphs are exchange bias, coercivity, and then a third important thing to note about these graphs is the sample's Néel temperature. So before I analyze each individual graph, let me explain to you what the Néel temperature is. So our magnetic thin films have this specific temperature. When they're heated up past this temperature, their magnetic or their atomic spins go from diamagnetic and aligned to random because of the thermal fluctuations. So in order for exchange bias to occur, you need to heat the sample up past its Néel temperature. So for the samples that we are working with, which were nickel and nickel oxide, the Néel temperature is 227 degrees. So if exchange bias occurs in the substance, the curve shifts to the right along the horizontal axis. So we can see that for 200 degrees Celsius, below the Néel temperature, the curve is centered at the XY intersection. For 210, we did actually see a shift to the right, which shouldn't have occurred had the sample been heated up to 210 degrees Celsius, but we have two possible explanations for this. Either because we're working with thin films on the nanoscale, the particles are so small that they're more greatly affected by thermal fluctuations, or the other reason for this misrepresentation of the trend that we should have seen is because the thermocouple didn't accurately measure the temperature. But again, we can see that the trend is restored for 220 degrees Celsius below the Néel temperature. We see that it's centered. 230, we see a shift to the right. 240, once again, a shift to the right. And also something important to note is the thickness of these curves, which represents coercivity. Coercivity is basically when you take a magnetic substance and you apply a field to it to its saturation point when all of the spins are aligned in the same direction. Coercivity is the magnitude of the field that would be required to bring the substance back to zero magnetization. And we see an increase in coercivity as a function of increasing temperature. Except for 250 degrees Celsius, we see a very small coercivity, and the reason for this is because at such high temperatures, your sample starts to oxidize, and that causes a decrease in coercivity. And yeah, so those are our results, and to expand on that, Sal's going to explain to you the conclusions and what all that means.
Okay. So some of the challenges we faced along the way were conflicting schedules, which didn't allow us to use the squid room. We also had another piece of data shown here at 220 degrees Celsius, which showed much too high coercivity for the temperature it was at. So we decided to test the sample at that temperature again, and the trend was restored. And the reasons for this were the same as the ones that Andrew explained. Some of our accomplishments include completing a literature review where we all read a multitude of papers where we learned about nanomagnets, coercivity, exchange bias, and everything to do with what we're doing. As you see in this picture, this surface is atomically smooth, but when we increase the temperature too high, it starts to become rigid, which changes the magnetic moments. And we also, taking this into account, found the ideal temperature for exchange bias in memory devices where the structure remains smooth and doesn't have a high coercivity. We learned all about how nanomagnets are influenced and the consequences of heating it up too much or not knowing the exact temperature at what our sample was heated to. In these two shapes, we see that the magnetic moment follows the long axis of the particle. Finally, we learned that engineering is interdisciplinary. Although we were in a mechanical lab, we were learning about magnetism, which is mainly something that electrical engineers do. And this shows that your major doesn't restrict what you will be doing in the future. And with our research, we saw that the future will be focusing on nanoparticles and making everything more efficient and more compact. We'd like to thank Professor Carman for supervising us and allowing us to use his lab, and our advisor, Wei, who's here watching us today, for teaching us everything we know. Everyone in the Active Materials Lab for allowing us to use their lab. Audrey, Rick, and Sherry for giving us this wonderful opportunity. And here are the references of all of the papers we read to learn about everything we know. Any questions?
All right.